Hello, everyone, and welcome back to another one of the online causal inference seminars. We are very happy today to have Samuel Wang from Cornell University, who will talk to us about uncertainty quantification for causal discovery. After the talk, we have a discussion by Daniel Malinsky from Columbia University. The Q&A today, the questions will be handled by Emma, so I'm switching over to her.
Thanks, Georgia. Yes, so please submit your questions throughout the talk. As soon as you have it, please submit it through the Q&A. Please use Q&A to submit the questions, because if you submit on the chat, not everyone can see them. At some point, Sam, I will stop and take some questions, and I will ask them for you. Yeah, so please do submit questions as soon as they come for you. All right. So that's kind of it. I'll let Samuel take over.
That's great. Is it the screen is showing all right?
Yep.
All right. Well, thanks for organizing this, and I'm excited to be here and to talk about this work. So this is joint work with Milan Kohler at the University of Chicago and Matthias Sturton at TU Munich. And so this is a project that we have been talking about off and on for probably about 3 or 4 years now. And so I'm excited to kind of finally talk about this and kind of share some of this work with you today. All right, so today I'll be talking about causal discovery, and I want to first provide a bit of motivation. So this figure is now a classic example from a paper by Sachs et al., which appeared in Science in 2005. So it depicts a protein regulatory network, and so you can think about this in the way that proteins interact within a biological cell. All right, so this figure, you can think of this as a graph which encodes causal structure, and each of these nodes represents a type of protein, and the arrows indicate some sort of causal effect. So in particular, for instance, we have this protein PLC gamma. This is a protein PIP2. There's a directed edge from PLC gamma to PIP2. And so what this encodes is that the prevalence of PLC gamma has a causal effect on the prevalence of PIP2 within this biological cell. So in this paper, this is called the consensus network. The authors call it the consensus network, and what they mean by this is that the structure is informed by many different experiments that were designed and performed by a lot of expert biologists, which were published in a number of papers, and over the course of many years, all of this information kind of coalesces into this plot here. So this is a long, tedious, expensive process, right? And this is exactly the type of situation where we hope causal discovery can be helpful. And just kind of at a very broad level, what I mean by causal discovery is the problem of estimating causal structure, or in some sense, selecting a causal model from data. And this is typically observational data. All right, so throughout the talk, we'll use the language of graphical models. And so basically we're using complex systems, we're representing a graph using a complex system using a graph, where each vertex represents a variable and each edge represents a dependence relationship. So in this case, we have maybe an observed vector, which has 4 elements, and this could be a corresponding graph. So if P has a direct effect on some other node C, then we'll put in this edge and we'll say P is a parent of its child C. So in this case, there's a directed edge from 1 to 3. You can see this right here. And so we'll say that Y1, or node 1, is a parent of node 3. If there exists a directed path from, say, node A to node D, then we'll say A is an ancestor of the descendant D. So in this case, we have a series of edges, 1 to 3 to 4. So in this case, 1 is an ancestor of its descendant 4. Throughout this talk, we're going to assume that the model corresponds to an acyclic graph. And so what that means is we can't start at one node, follow a series of edges, and then end up back at that same node. Okay, so under this assumption, this implies that there is always at least one causal ordering for the nodes. And what we mean by this is an ordering or permutation of the nodes. And we're going to use theta to denote an ordering or permutation. In particular, theta u will be less than theta v, where u and v are two different nodes, only if u is not a descendant of v. So in this case, a valid causal ordering would be 1, 2, 3, 4. But we also have another valid causal ordering, which would be 2, 1, 3, 4. So you can basically think of this as just an ordering where nodes which appear at the front are kind of causes in some sense, and then causality flows downstream towards nodes at the end. All right, and so just kind of a bit of notation here, we're going to use PA of V, DE of V, AN of V, and ND of V to denote parents, descendants, ancestors, and non-descendants of V. Okay, and then finally, we will let PR of theta of V. You have some fixed theta, fixed ordering. And so this could be a valid ordering or it could be an invalid ordering, but it's just some ordering. And PR of V will denote the sets of nodes which precede V. And basically, they're just the nodes which are before V in that specific ordering. All right, so in causal discovery, we don't assume that this graph structure is known a priori, right? And this graph structure is actually what we want to estimate from the data. All right, so this is a very broad topic, but roughly speaking, the place where most problems start is with identification. So the question is, what do I need to assume such that I can pick out the correct causal model given population values? Or you can think of this as maybe having an infinite amount of data. Right? And so the way that this is done is people assume that the true data generating procedure lies within a class of models that's small enough so that causal structure can be identified, but large enough to reflect the true process. And so the thing to think about here is like the assumptions that we make, the identifying assumptions, end up being very, very important. And I'll mention a specific type of assumption which is used later. The natural follow-up question is about consistency, right? So under various assumptions, how can I consistently recover the causal model from sample data? And so there are many different procedures under various assumptions which have been shown to be consistent. But these procedures, and kind of by and large, take in data and output a single point estimate of causal structure, right? And so this might be a graph, this might be a causal ordering, this might be an equivalence class of some sort, but it's kind of a single point estimate. And this, however, until pretty recently is where most of the literature, and I should say at least from a frequentist perspective, has stopped, right? So it's clear that identification and consistency are very important, right? And kind of the things that you want to think about first. But as a statistician, I think it's also critical to be able to assess our uncertainty about the causal model that we've estimated. So put another way, how much confidence do we have in the estimated causal structure? Right? And so even if I do have consistency guarantees, and even if my, given a specific set of data, the estimated structure can be incorrect. And this might be because of sample variability. This might be because I've made incorrect assumptions and my model is misspecified, or it could be both. Right? And so this is kind of the problem that I want to think about today. And so ultimately, I want to think about uncertainty in the causal model selection problem. All right, so perhaps uncertainty about model selection isn't quite as natural to kind of think about as first. So let's think about confidence intervals we're used to, right? Let's suppose a coefficient in a linear regression problem. So certainly we can start with the mechanical definition, right? So you repeat this procedure with new data many different times, and so on and so on, right? But in practice, what questions does a confidence interval actually inform us about, or what does it actually tell us? Right, and so maybe kind of broadly speaking, there's kind of two questions at least, right? So how trustworthy is my point estimate? What are other possibilities which are not ruled out by my data? right? And so the width of the confidence interval might tell you how trustworthy your point estimate is. If it's quite wide, I can know that I don't have a lot of precision in my estimate. And moreover, not just the size of the confidence interval, but I'm actually probably also interested in the specific values contained in the interval, right? And that tells us in some sense, what are other possibilities that are not ruled out by my data? So our work aims to provide answers for these two questions in the context of causal discovery. So I should note that there's been some recent work on hypothesis testing of individual edges within the graph, or in some cases, a set of edges. But these procedures require that the causal ordering is known, or at least can be recovered consistently. And so in general, we don't actually know whether the causal ordering can be recovered consistently. And so we're interested in providing uncertainty over the entire causal structure, which is valid even when the causal ordering can't be consistently recovered. And the way that we'll do this is by proposing a framework which produces confidence sets for the causal ordering itself, right? And so we're kind of taking a step back, not looking at edges, but kind of thinking about the case where we might have even less information. All right, so before I dive into the specific procedure, I want to talk briefly about the types of models that we're actually considering. Right? And so as I mentioned before, there are various assumptions which allow for identification of causal structure from observational data. And I want to talk about one specific model here, the linear structural equation model. So this model assumes that each variable that we observe is a linear function of its parents in the corresponding graph, and some idiosyncratic error term. We'll also assume that there's no unobserved confounding in our system, and mathematically we'll encode that by the mutual independence of each of these error terms, these epsilon terms. All right, under these assumptions, Shimizu et al. In 2006 show that when these epsilon error terms are not Gaussian or non-Gaussian, the exact graph corresponding to the data generating procedure can be identified. And this is from observational data. So we'll mostly, and then this talk will stick with the linear setting for simplicity, but I do want to note also identification was shown for nonlinear structural causal models by Hoyer et al. And Peters, and there's a series of papers there. And our procedure also directly generalizes to nonlinear models, but we'll stick with linearity on the linear model for simplicity here. Okay, so if you're not familiar with the literature, what I told you might seem like a bit of science fiction, right? So how do non-Gaussian errors help us identify causal direction, right? How do they help us identify the exact causal graph? And so here's a bivariate example to hopefully build a little bit of intuition. In this case, there's two variables, and the true graph is, I have two variables, P and C, and the true graph is P is a parent of its child, C. Right, and so you can see this, that C is a linear function of P plus some error term. And I should also note that the errors are generated from a uniform distribution. Okay, so say I'm trying to decide whether P is a parent of C or whether C is a parent of P. In both cases, I can plot the positive parent on the horizontal axis and the positive child on the vertical axis. And so that's what I've done here. Left-hand side, I have the correctly specified graph. Correctly specified model. On the right-hand side here, I have the incorrectly specified model. In both cases, the red line indicates the least squares line. And if you just look at this plot, it may be a little bit hard at first to kind of see how you might differentiate between the incorrect model and the correct model. But here on this next plot, I've plotted I've kept what I think is the parent on the horizontal axis. And here I've plotted the residuals when I regress the child onto the parent. And so now we can see things that are a little bit different. So here on the left-hand side, where I have the correctly specified model, we can see that the residuals are roughly independent of the parent. On the right-hand side, where I've incorrectly specified the model, we can see that the residuals are uncorrelated with the parent. And this is from the first order conditions of least squares, but we can see that they're not independent. And we can see this by noting that the domain the range of the residuals changes as I go across different values of what I thought was the parent. All right, so the punchline here is that by checking independence of the residuals and regressors, I can rule out false models and certify correct models. And this basic intuition actually also holds in multivariate data, right? So if you give me some node V and a set U, I'm going to let eta VU be the residuals, which result from regressing in a population setting V onto U. And so what we mean here is population setting, right? We're going to use the coefficient which would be produced by the OLS coefficient, which would be given by using kind of the population covariance. All right, if U contains the parents of V and does not contain any descendants of V, then the model that I've just described to you, this linear structural equation model, under these assumptions, then the residuals will be independent of the regressors. And in general, independence does not hold if this same independent statement does not hold if U contains descendants of V, or if the parents of V are not contained within U. Okay, so this statement I'm about to make is not quite true, but at least to build into intuition, I think it's helpful to think about this. And so one can think of the independence of the regressors and the residuals as equivalent to the fact, to some sort of ancestral statement. In particular, the statement that U contains the parents, but does not contain any descendants of V. So we can, so this is not quite true, right? There's a lot of subtlety here, but at least for the purposes of this talk, I think that maybe will be helpful to think about it in that way. All right, so I'll pause here for any questions.
Hi, Sam. There is one clarifying question from Alexander. Do I understand correctly that the causal ordering is not necessarily a total ordering on the set of nodes?
So the way that we're thinking about it, it is a total ordering, but there may be but there may be multiple valid causal orderings. Yeah, so we're thinking of an ordering as being a total ordering, but there may be multiple orderings that are valid.
All right, but you select kind of one, I guess. Yeah.
Sure, yeah.
All right, and there's another question that just came up. In your example for intuition, how do you separate misspecification from non-constant variance? Looks like you would get the same diagnostic. What assumption are you making so you can distinguish the two?
Yes. So you're right. So this kind of statement here, which again is not entirely correct, but roughly speaking, is the intuition that I want to build. So you're right. So we've specified a linear model, and we've assumed that each of these epsilon v's are IID and independent of these YUs. So you're right. If there's a violation to this model assumption, then it would also this identification kind of criteria would not be totally correct.
Great. Those are all questions for now. Thanks, Sam.
Okay, great. So given this setting, right, so then the question that we want to answer is how can we form a confidence set for the causal orderings? Which gives us a way to assess uncertainty about our point estimates, right? And the framework that we're going to be using is actually very, very simple, right? So if we let theta be a causal ordering, or you can think about this as a permutation of my nodes, we're going to suppose we have a goodness of fit test for the causal ordering. And this produces some p-value, which we'll denote pi of theta. Now to form the confidence set, which we're going to denote hat theta, we're going to simply invert this goodness of fit test. So put another way, for some pre-specified alpha, let's say 0.05, hat theta contains all the causal orderings which are not ruled out by a goodness of fit test at level alpha. All right, so this is very straightforward. There's nothing too complicated about this, and assuming we can kind of compute or get our hands on this object, a question is, why should you care about it? So if you recall the questions about uncertainty that I brought up at the beginning, which we wanted to answer, right? So first one, how trustworthy is my point estimate? And what are other possibilities which are not ruled out by the data? Right, so for instance, if hat theta is empty, so if my confidence set is empty, this means that no orderings satisfy the identifying assumptions. Right, and so this should cause the scientists to be very cautious and potentially think about using a different causal discovery procedure, which requires different assumptions. Right. On the other hand, if hat theta is very large, and particularly if it contains many orderings with conflicting causal relations, this might mean that the signal, in some sense, is low. Right, and so the point estimate that you might have gotten from your procedure might be, or probably is, unreliable. And it could potentially change drastically if new data was gathered and this experiment, in some sense, was repeated. So this set tells me a lot about how trustworthy my point estimate might be. In terms of the second question, right, what are other possibilities which are not ruled out by my data? This set is kind of explicitly that set, right? It's exactly the set of orderings which are not ruled out by my data. And so we think this could be quite helpful for hypothesis generation so that scientists can better know which experiments to perform and to investigate further down the line. All right, so more formally, what can we say about this object, right? So if we let theta g be the set of all valid causal orderings, right? And so these, again, to the question earlier, these are all total orderings, but there may be multiple orderings which are valid. When the goodness of fit test that I'm using is asymptotically valid for any of the thetas in this true set of orderings, theta g, then we can make this statement here, where the intersection of the confidence set that I've produced, theta hat, and the true set, theta g, is non-empty with some user-specified probability. I mean, in some ways, it's probably a bit more natural to make a statement about the probability that the true set would be contained within the estimated set, so something like this. But since we don't limit or kind of know a priori the number of valid orderings, it becomes a little bit harder to make a statement like that. I do want to point out that we focus on orderings largely for computational reasons because the search space of orderings is much, much smaller than the search space of graphs. And this is this kind of strategy has been used before. But in general, consistently recovering the graph when you start with the correct causal ordering requires much weaker conditions. And so when those conditions are met, what we can do is we could take each ordering in theta hat and map it to an estimated graph. And then letting those set of graphs be g hat, then this would give us something kind of much more natural in terms of what we are kind of used to thinking about in terms of confidence intervals or confidence sets. And so in particular, the true graph g, which in this case is unique, is contained within this set with some user-specified probability. All right, so another nice thing about this set theta hat is that it's also of interest because it can give it a conservative set of ancestral relations. And so this is similar to the notion that was proposed in Peters et al. In 2016. And so if we let A be a set of pairs of nodes in my graph, and A is going to include the pair UV only if U is an ancestor of V. Right, so this is something about the true graph here. And if I can construct this set A hat, right, to be the set of pairs, which I include UV in this set, only if U precedes V in every ordering that's in my set, then I can make the statement here that A hat is included within A with some user-specified probability. Right, and so I'll put another way, this set A hat does not contain any false discoveries with probability 1 minus alpha. Okay, and so this is similar to what is proposed in Peters et al. 2016. All right, And then finally, I want to point out that this confidence set can also be used to get confidence intervals for causal effects of U on V, which account for model uncertainty. All right, so suppose, so we're still using this kind of conservative set of ancestral relations. And so suppose I estimate theta hat with confidence level alpha over 2, and I have some pair UV which lives which is contained in A hat. Okay, so then for each theta in theta hat, so each ordering in my confidence set, I can form a 1 minus alpha over 2 confidence interval for either the direct or the total effect, given this specific theta. So for the direct effect, perhaps you would regress V onto all the nodes that precede V, and this again should include U by assumption. For the total effect, I might regress V onto all the nodes this should say precede U, including U. Right, and so you can get a confidence interval for the linear coefficient, which corresponds to U, and this is just kind of the normal linear regression confidence interval that you might get. But if you get each of those confidence intervals and you take the union over all theta, so you're going to get a fairly wide confidence interval in some sense. This then forms a confidence interval which for either the direct or the total effect, which accounts for your model uncertainty. So this is similar in some sense to the problem that was considered by Strider et al. Okay, so we started off with a pretty simple procedure, but hopefully that quick overview and kind of some of those like maybe applications or use cases convinces you that this object that I've just kind of mentioned is interesting and useful. But that leaves us with the question of how do I practically compute this object? Right, so there are 2 parts that we need for this simple framework. The first of which, the goodness of fit test, is largely a statistical problem. And the second part, inverting this test, is largely a computational problem. Right? And so the solution to both of these parts are tightly interwoven in some sense, but somewhat distinct. Okay, so let me then stop for any questions before I dive into the details.
Hi, there is one question in the Q&A. So it says, in an RCT, you know the causal order, and yet the goodness of fit may be lousy. Why does a proper causal order imply a good fit and an improper causal order imply a bad fit?
Yeah, so I guess maybe to the first part of the question. So in an RCT, you know the causal ordering, but we're not just so somehow the test that we're going to specify, right, doesn't just test for causal ordering. It tests for the causal ordering as well as the specific modeling assumptions that we've made. So you're right. It could still be that, you know, if linearity is not the right model, then this goodness of fit test will still reject, even though the causal ordering may be correctly specified. There was a second half of that question as well, I think, right?
I guess the question was, yes, why does a bad causal ordering imply a bad fit or something like that? So yes, I think you answered it, but why does a proper causal order imply a good fit and an improper causal order imply a bad fit? I think, yeah, you say that there's more to it than just a causal order. Yeah, so those are all the questions we have for now. Please do submit your questions. Sam, we're about halfway through the talk, just so.
Okay, great. Okay, so for some ordering theta, so now I'll talk a little bit about the details of the goodness of fit test and how we're gonna try to do this computationally. Okay, so for some ordering theta, recall that this notation PR of V denotes the nodes that precede V in an ordering theta. Right, and so again, this could be a valid ordering, this could be an invalid ordering, but it's just some ordering that we've specified. And where again, we're going to let eta v and then set minus the PR of v be the population regression residuals when regressing v onto PR of v. Okay, so what I showed you kind of roughly speaking from the small example before, when theta is a valid ordering, this is equivalent to these ancestral conditions here, right? So the ancestors of v are contained within the predecessors of v, and the predecessors of v do not include any descendants of v, right? So this is kind of the definition of a valid total ordering. And I should say this is true for all v. But from the example that I showed you earlier, this statement about causal ordering or something about the graph implies that these residuals are independent of its predecessors for all v. Okay, so this then gives us a way to test for a valid causal ordering. In particular, we're going to test whether the residuals are independent of the predecessors for all v, and we're going to use this as a proxy for testing whether theta is a valid causal ordering. Okay, so if I just think about for a specific v, a specific node in my graph, and I want to do that test once, this then kind of yields the very straightforward but slightly naive procedure where we're simply going to regress v onto its predecessors. We'll form the residuals, and again I have a hat here because these are the estimated residuals in some sense because I'm using an estimated linear coefficient. And then once I have the residuals, I can just apply any independence test you like to test whether the residuals are independent of the predecessors. Okay, so unfortunately, this problem is a little bit more complicated than that. And I'm not going to dive into too many of the details here, but I want to at least point out a little bit of the subtlety. So in practice, to get the residuals, right, we need to estimate a linear coefficient, these, and we do this using sample data. So what this means is that the linear coefficients, in some sense, you can think of them as nuisance parameters. And when I don't have them exactly correct, right, I can think about the estimated residuals now having some term which actually includes the predecessors of v, even when the null hypothesis is true, that I've kind of correctly specified the causal order. And so what this means is that even when this statement holds in the population case, even when the predecessors of v are independent of the population residuals, it's not generally true that this statement, when I'm using the estimated residuals, the estimated residuals are generally not independent of the predecessors. And in fact, if you use kind of whatever test of independence that you're trying to use, if it has power against these local alternatives, then this naive procedure will not have proper size. Okay, so fortunately, we're not the first ones to notice this, and there's a lot of existing work which addresses this issue of goodness of fit testing for linear models via testing independence of residuals and regressors. And what I want to say is in practice, you can use any of these procedures in our framework, and you might need a slight modification here or there to kind of plug them in. But really, this is kind of, there are many situations in which one of these tests might be more appropriate than the other. Nonetheless, we've developed a procedure which I'll only mention here at a very high level, but we've developed this procedure in a way that we hope melds together some of the kind of the better elements or the best elements from previous procedures, which are particularly useful here in our setting. So in particular, we use a test statistic, which is a scaled sample mean of the product of a nonlinear function. So G is a nonlinear function, and it takes in one of the predecessors of V, and then eta here is the residuals. And so we're thinking about scaled sample moments of this form. All right, and so one of the reasons that we use this test statistic is that we'll need to compute this test many different times. And so we want something that's quite computationally efficient, right? And so when G is a polynomial, This has the flavor in some ways, which is similar to the higher order moments, which are examined by Schultheis et al. And Wang and Dirt in 2019. And this is one of the nice things about the test statistics that are used by Schultheis et al. Is that they're very fast, and so we kind of have that element here. Schultheis et al. Calibrate their test by deriving a limiting normal distribution. But in contrast, we hope to get better finite sample results by using a residual bootstrap. And so in some ways, this is similar to work by Sen and Sen 2014, who use a very powerful but computationally expensive Hilbert-Schmidt independence criterion as their test statistic. Okay, so the Sen and Sen procedure, they use a residual bootstrap, which resamples both covariates and residuals to calibrate their null. And so in some ways, they're thinking about the joint distribution of their test statistic over both the covariates and the errors. And in contrast, we want to condition on the covariates, right? And so this, as we'll talk about in a few slides, this allows us to produce tests which will be independent across each level so that we can combine the results in a way that doesn't lose as much power. And so stylistically, this is similar in some ways to the conditional test, which have been brought up by Shaw and Bullman and Barrett and Samworth. But in those works, instead of using a residual bootstrap, they propose a parametric bootstrap. And kind of in practice, they assume that these errors are Gaussian. And so this is, in our setting, is kind of exactly what we want to avoid. And so hopefully we've kind of taken a lot of these previous procedures and kind of picked out what's best or most useful for our specific setting here. And built this into a new procedure. But like I said, there are lots of different situations depending on your scaling of P and N and things like this, and where you might want to use other procedures which have been previously proposed. Okay, so like I said, I'm not going to really dive into the details of the goodness of fit test for a single regression so much, but once you have one, it's very straightforward to apply this test to the entire ordering. Right, so what we're going to do is we're going to apply the test to each node in the ordering, and we'll get a p-value for each test. And the p-value will be this gamma theta b. And we're going to combine all the p-values into the single statistic by just taking the minimum. And so this is sometimes known as Tippett's rule or Tippett's method. And as I mentioned earlier, we have our procedures specifically set up in such a way that we can show that these p-values are asymptotically independent. And so what we do is we compare gamma theta, this aggregate or through the minimum, to a beta distribution, to the quantiles of the beta, and this gives us a final p-value pi theta. Right. Okay, so very concretely, what do we do? If we're testing the ordering 1, 2, 3, 4, what we'll do is we'll first consider the node 2. We'll look at its predecessors, which are y1. So we'll regress 2 onto y1. We'll look at the residuals and test whether they're independent, and this will produce gamma theta 2. We'll do this again for 3 with its predecessors 1 and 2, and again for 4 with its predecessors 1, 2, 3. We'll take the minimum of all these p-values, and then we'll compare that minimum to the quantiles of a beta 1, 3 to get my final p-value pi theta. Okay, so what we can show is that using our specific testing procedure, when the elements of epsilon are mutually independent and sub-exponential, as long as p, which is the number of variables that I have, log p over n goes to 0, then essentially we have a valid test, a goodness of fit test for the causal ordering. So this is, again, like I said, I'm going to mostly focus on the linear case. You can think about the nonlinear setting, and the way to think about this maybe is just to use a sieve estimator to model the nonlinear function, where we have a basis of functions which we allow to grow with our sample size, and we just track the approximation bias through. Okay, so that's kind of the statistical part of the problem. But how do we do this kind of computationally, right? So the number of orderings that we would need to test is huge, right? And so how do we make this feasible for at least a moderately sized P? And so to do this, we'll use a branch and bound type procedure. Right? So the final test statistic that we're using, gamma theta, is the minimum p-value across the tests for each level. But for a pre-specified p, which is the number of variables I've observed, and alpha, we can compute the critical value as the alpha quantile of a beta 1 p minus 1. And so when we're testing level by level, we can actually stop once the critical value is exceeded. So what I mean by this is, suppose I have a case where I have 10 variables, I've set alpha to 0.1, then the critical value is 0.0116. So let's say I'm testing the ordering 2, 1, 3, 4, 5, 6, so on and so on. So I get to the first thing that I'm going to test. I'm testing 1 and its predecessors 2. And say on this first thing that I'm testing, I get out a p-value of 0.009. So I know I've already exceeded the critical value, and I can reject this ordering without going down the rest of the way. And not only that, I can actually automatically exclude all orderings which start with 2, 1, and then anything else. Right? So this allows me to rule out a lot of orderings without doing the full computation. Okay, so practically speaking, we use a procedure which starts with small orderings, in this case, orderings of size 2, tests them all, and then takes all the non-rejected orderings and tries to see if we can continue kind of building on, and goes to orderings of size 3 and 4, and it continues testing these orderings until I get, I've tested and verified that the total ordering is not rejected by the goodness of fit test. One other kind of computational thing that we can take advantage of here is that when considering ancestral sets, the ordering does not necessarily matter. And what I mean by this is, suppose I'm considering the orderings 1, 2, and 3, and 2, 1, 3. Right? So if I'm testing node 3 in this case, I want to test whether the ancestors of 3 are contained in the predecessors of 3, which is contained in the non-descendants of 3. For both of these orderings, the test that I would do is exactly the same. Right? So the punchline here is, at each step, I need to record a test statistic for each permutation, but I only need to compute a test for each combination. So this also allows, this kind of still is definitely a memory constraint, but in terms of a computation, this allows us to reduce and to avoid redundant computation. Okay, so I'm going to briefly talk through a little bit of a few simulations, and so getting close to the time, but so we're going to consider linear structural equation models here, and we're going to set p equal to 8. So this is, a small but moderately sized graph. And we're going to consider a few settings where we have n, the number of samples, grow from 500, 1,000, all the way up to 5,000. And so we're generating a random graph with edges basically put in with some constant probability, but we are drawing the edge weights, or in this case, the linear coefficients in my structural equation model from a gamma, and we've specifically constructed this so that the signal also decreases with the sample size. And we're drawing errors from various distributions, gamma, Laplace, log normal, uniform, and Weibull. Okay, so the first plot here, this just kind of verifies what you would expect, that we can create confidence sets which do have the correct coverage. And these are all 90% confidence intervals with roughly the, yeah, and so you can see that each of these has roughly the correct empirical coverage as we go through. And so on the horizontal axis, I have various sample sizes. Each of the different colors indicates different distributions. Okay, so this is maybe a more interesting plot here. And so on the solid lines here, and each of these, again, each of these colors is a different distribution, but these solid lines indicate the proportion of orderings in my confidence set out of all of the total orderings that are possible, right? And so you can see when I have at n equals 2500, my confidence set only contains a small portion of the total orderings that are possible. The dotted lines here in this on this plot indicate the proportion of times that I can consistently recover the true causal ordering, and this is using the direct Lingam procedure. Right? And so the punchline here is that even, and you can see that these are kind of by design, we've set up the simulation settings to explicitly in this way, that the true causal ordering is not consistently recovered. Right? And so these are roughly about 20% of the time. And so we can see that the confidence set is shrinking down and it has the right coverage. And so it's doing the right thing, even though I can't consistently recover the true causal ordering. And here we have another plot which shows basically that the ancestral relations that we can recover with this conservative set of ancestral relations, A hat, is also increasing despite the fact that I cannot consistently recover the causal ordering. And then finally, there's a question maybe about timing, right? The other thing is this computationally feasible? So we showed kind of in all those simulations with P is equal to 8. Here we kind of ramp up the size of the graph a little bit. We go from 10, 11, 12, and 13. And so this is the time, average time to compute a confidence set. And this is done all on a single core. So you can also think about how you might parallelize this and speed things up. But maybe the thing to think about here is even at P equals 13, we can create a confidence set in roughly about an hour on a single core. Now, again, I do want to point out that this is dependent on the quote unquote signal, right? We're using a branch and bound procedure, which in worst cases has to search over all permutations. And so in some sense, when the signal strength is larger and I can rule out more orderings near the beginning, then this also allows us to do faster computation. Okay. So I will briefly end with a little bit of discussion. I'll go quickly here because I know Dan has a lot of these thoughts also. We've proposed a procedure which returns a confidence set for causal orderings. Computational feasibility is definitely a constraint, but it depends on the signal to noise ratio and is generally feasible for, I'm using the term medium size P, although I know medium is maybe relative here. But kind of very importantly, it allows practitioners to see whether the identifying assumptions used for causal discovery are reasonable for their data or not. And it also allows practitioners to see what other orderings are not ruled out by the data. So the drawbacks, I think there are many, and I want to be honest and forthright about this. And so inverting the absolute goodness of fit test may rule out orderings even when they are very helpful. And so I'll be brief here because I know Dan wants to talk about this as well. But you can imagine the case where I have an empty confidence set and I've ruled out all orderings, but it could be that the misspecification is still mild enough that the point estimate that you get is actually still useful, right? And so it could be that you have an empty confidence set, but the point estimate is still useful, and this is maybe a drawback. And there are ways to get around this, but what I would say is that we actually don't know in these settings how quote unquote mild the misspecification is, right? And so it could be that you are in the case where it is still, the point estimate still is useful, but you could be in the case where the point estimate is completely useless. And so at least knowing that the model specification is not true is helpful. And then the last drawback, right, this is very computationally intensive. And so you can parallelize things, but and speed up. There's a few tricks that you can do to speed up things, but this is still kind of one of the big bottlenecks. Okay, so the future questions: can confidence sets be extended to different models? And can we think about different notions of confidence sets? So I'll actually not discuss that because I think Dan has some good thoughts on this, and so I'll turn the time over to him.
Awesome. Thank you for your discussion. I think we are ready for Dan, and we can take the questions if we have time afterwards, since we're running a little bit behind. I want Dan to have all of his time. You don't mind stopping sharing your screen?
Yeah, let me just pull my slides up. Okay, this looks okay. All right, great. Thanks so much to Sam and to the organizers for inviting me, and congrats to Sam and the co-authors on a really interesting and insightful paper. I think there's a lot of really cool content in here. So I will try to be brief and just highlight a few things that I think are really valuable and the questions that I think that they raise from this kind of paper. There's sort of three things that I kind of want to highlight. The first is that I think it's really important to orient the community, the causal inference community and the causal discovery community towards quantifying uncertainty in causal model selection. And so I'm really happy that this paper is doing that, and there's a lot of work to be done, and I hope more people get inspired to come up with confidence or sets or quantifying uncertainty in different ways. I think this idea of inverting a global goodness of fit test to construct confidence sets for entire orderings or models is quite interesting. And I know that similar things have been done in other areas of statistics that require confidence sets for kind of unusual statistical objects, but I don't think it's really been done in this particular setting before. And I think that the talk and the paper associated with this talk do a good job of highlighting many questions and choices that arise when quantifying uncertainty in these kind of non-standard statistical objects. And Sam and his co-authors provide answers to each of those questions, which I think are reasonable answers. In many cases, there are other answers that may also be reasonable, and so that's what I just want to highlight here. So the first thing I'll say is that most theoretical work about the statistical properties or statistical performance of causal discovery algorithms has so far focused on consistency properties of point estimates, where the point estimate is a graph, which may itself represent a set of graphs being an equivalence class. But there's this extensive literature on the conditions under which you can get different kinds of guarantees, point-wise guarantees, which are kind of weaker, and uniform consistency guarantees, which are kind of stronger under various assumptions. And this is just a kind of partial list of papers over the last 20 years or so that I think have tried to tackle this problem in one way or another. A key takeaway of a lot of that literature is that strong guarantees or strong conclusions will necessarily rely on strong assumptions about the data generating process. In particular, uniform guarantees are going to be stronger than point-wise guarantees. And to sort of like roughly summarize what goes on in this literature is that we can achieve uniform consistency guarantees for the equivalence class, for estimating the equivalence class in non-parametric settings when we make strong assumptions like what's called strong faithfulness or the somewhat weaker assumption called K-triangle faithfulness. But if we make only relatively weak agnostic assumptions, just using regular faithfulness, for example, we can typically only expect point-wise consistency guarantees. And in this case, Sam and his co-authors, they're drawing strong conclusions by giving you asymptotic confidence sets, which are closely related in a kind of complex way to uniform consistency guarantees, but they make strong assumptions to do that. I won't go into the relationship. I think if I'm understanding correctly, the confidence sets that Sam and his co-authors present are uniform, although you can correct me if I'm wrong about that. But in any case, they do rely on this kind of additive noise model assumption class in order to get a unique graph or ordering for every, they rely on that assumption in order to get identification of an ordering or a graph, which might be a set of orderings. And this additive noise model, for which the linear model is a special case, does allow that, but it comes with some drawbacks. Any assumption that whether it's a Lingham model, a nonlinear additive noise model, or one of these equal variances type models that ensures unique identifiability of the causal structure is a quite strong assumption. It's going to lead to these strong guarantees, but it's going to be potentially easy to violate. And in particular, the additive noise model class is not closed under marginalization. So if you start with a set of variables V and you think you have some additive noise model that's nonlinear over V, and then you look at any subset of V, call it V prime, which might be from marginalizing out mediators or marginalizing out confounders, you're no longer guaranteed to have an additive noise model over that smaller set. And so in practice, any set that you give me I can think of as a marginalization of some bigger set. And so one would never really expect, I think, this model class to exactly hold for any given set V. Although people, reasonably might think that it's a good approximation in some particular setting. I think that it's worth highlighting here that it can be concerning because the null hypothesis test that's being tested over and over again in this approach presumes this model class actually holds. And so if it only really approximately holds or doesn't hold at all, then we'll have grounds to reject those null hypotheses quite often for reasons independent of the causal ordering. So my first question to Sam and to his co-authors is about whether we can do something kind of similar in spirit, but in a kind of non-parametric general way, working in the space of equivalence classes. So once we move away from these additive noise models and into the kind of non-parametric generality, we won't be able to have a unique identified DAG or the orderings that go with that. And so we have to start thinking in the space of equivalence classes. And I think that probably the answer is yes, but it's going to introduce some additional complications. Related to my second bullet point early on, I think the idea that Sam is using about testing global goodness of fit tests is really interesting. I think this seems like a great way of constructing confidence sets for model selection procedures in general, and I think it ought to be explored more. The approach taken here is global in that they test many constraints for a given ordering. So for a given ordering, they're testing for each variable, basically whether the structural equation model holds for that particular variable given its predecessors. And then they aggregate the p-values and accept or reject the entire ordering or model at once. However, some particular null in that set of tested constraints may be false for many different reasons, even if the structure, meaning the ordering itself, is correct, as Sam mentioned. You could have the wrong functional form for your estimated F. You could have non-additive noise. You could have residual correlation between things. And so this leads me to ask whether we can do something similar in spirit, but test a non-parametric independence constraint implied by the ordering rather than this kind of more additive noise model specific kind of constraint. Although as I was listening to Sam's talk, I realized this one that I wrote down specifically is probably not the best way to start. So the Markov property for a DAG says that every variable is independent of its non-descendants given its parents. So you might think that for fixed ordering, I can just use the ordering to try and determine what are the non-descendants and what are the predecessors and do this kind of independence test. It's a bit tricky here because you don't necessarily know how to distinguish between non-descendants and things that are just less greater than in the ordering. So something more tricky would have to be done here, but something in this general space of testing the global Markov property or things implied by the global Markov property, I think would be quite interesting. And this ends up being closely related to work done by Carolyn Uhler and her collaborators on permutation-based search methods. Although they focus on they look through all possible permutations in a kind of computationally clever way, and they test these kinds of independence constraints, although they focus on returning a single best ordering rather than a confidence set. And a question that this leads me to is the benefits and drawbacks of a global p-value kind of based approach rather than local uncertainty quantification for parts of the model. There has been some previous work that's computed p-values for individual edges in a DAG by Strobel et al., which assigns basically a p-value to a single edge for each edge in a discovered graph using something like the PC algorithm or similar, which can indicate pieces of the graph that are more or less trustworthy based on the p-values. That approach is quite different from this one, and I think each of these might have some benefits and drawbacks in terms of how you're quantifying uncertainty for different use cases. And then I think this is my final question to Sam for consideration, is whether this general approach can be adapted to a certain confidence sense after using a consistent point estimation procedure. So if you use something like the PC algorithm or GES or FCI or whatever it is, that returns a single object to you, which might represent an equivalence class of graphs. And you might think that in analogy to this kind of like theta hat plus or minus, the walled confidence interval approach, that a confidence set might be something that's, minimal deviations from a point estimate that we think is the sort of our best guess at the graph. And so you might consider starting with that point estimate and then doing something like Sam's procedure, looking at goodness of fit tests for nearby models that are different by one edge or two edges or some sort of approach like that, which I think could be an interesting follow-up to this kind of work, and would have the benefit of including elements in the confidence set that are not just satisfying the coverage guarantee, but that are like plausibly satisfying the coverage guarantee, or plausible models, because they're close to our best fit, our best guess kind of thing. So I'll end there and let Sam have some time to wrap up. Thanks.
Thanks, Dan. Feel free to respond to some of the comments that Dan brings up.
Yeah, thanks, Dan. I really appreciate the discussion. I think we're totally on the same page. The hope here is that this kind of work spurs a lot of other folks in the community to think about these problems. And so, yes, I want to absolutely be very kind of forthright with the shortcomings and say, hey, come work on this, right? Because there's a lot to be done here. Maybe I'll kind of just, in terms of the questions, I'll go backwards to forwards kind of. So this kind of question about the walled type confidence interval. And so this is actually something I think there's a lot to that. And this is something that we kind of considered a little bit at the beginning. We kind of discussed a lot of different ways to think about this. And in particular, I think one of the nice parts of that is that this goodness of fit test rate, it could be that the model misspecification is somewhat mild, and so that your point estimate still useful and good, but would be rejected by a goodness of fit test. And so if you center your confidence interval around a point estimate, then you still kind of can get a non-empty confidence set in a way that's helpful, right? I think one of the things that we were a little bit kind of didn't quite know how to think about, maybe in this way though, is that you don't really know whether your misspecification is really bad or not. And so in some ways it could be a benefit that you still get a non-empty confidence set, but in some ways it could kind of lead you astray quite far. And so in another way also, you need kind of in some ways you need consistency of the point estimate to still kind of form good confidence sets. And so the procedure, we ultimately kind of decided to go a different way, so where you don't necessarily need consistency. But I do think there's a lot I think there are definitely ways, I think, in which that type of confidence set can be thought of and would be fruitful. Maybe the question about the kind of thinking about more local structure, that I think is actually, so I haven't read this Strobel paper from 2019, so thanks for pointing that out. And I'll definitely add that to my list of things to read. And this is in some ways also a little bit similar to some very recent work by Schultheis, Bullman, and Yuan, where they think about testing specific linearity assumptions in a graph. And I think there's, you're right, these are kind of complementary ideas, where local structure is important and global structure kind of are somewhat complementary. I think for us, it was, I think, at least if you assume a DAG, kind of the idea that if you flip an edge here, this doesn't just have local implications, it actually has kind of global implications elsewhere. And so I think that was one of the reasons that we kind of thought more about global structure, because it's not quite as easy just to kind of paste together a bunch of kind of confidence intervals to get one large confidence interval. But I think practically speaking, I think kind of having this local confidence sets would also be quite helpful. So, and then I think the last question was about kind of going more non-parametrically and thinking about equivalence classes. Yeah, definitely, right? Like, so yes, we've made kind of strong assumptions in order for our confidence set procedure to work. And in some ways, we came at it from the point of view of, I have used this procedure on my data. And so I've used a lingam or a continuous additive noise model, and I want to assess the uncertainty in this particular point estimate. And so one of the things that you want to know here is, are my identifying assumptions good, right? And so this allows us to test that. Now, if you take out for the non-parent kind of, if you're less parametric about things, I think one of the hard things that we were trying to think through a little bit is this becomes very computationally difficult. So in particular, when you have kind of a class of orderings that you can search over, this is much easier computationally, and then kind of the search over equivalence classes and specific graphs, then, as you know, can be quite tricky. And so I think there's definitely good work to be done in that area. And I hope either to do that myself or to see other people do that. So yeah.
All right, thank you both. Since we're running a little bit behind on time, let's wrap up here, and hopefully the audience will forgive us for not taking their questions at this point. So let me wrap up really quick. I know it will be to everybody's disappointment to hear that we're going on a summer break, and we will see you again in September.